Are there any questions from last time? So I'll ask again, like, is the rate okay? Is it too fast, too slow? Any comments? I can easily adjust. I don't know how to interpret that. So what have we done? We picked one system and we analyzed it from a number of points of view, and we'll continue to analyze the same system from a number of points of view. And we gradually extract lessons, and many of these lessons that we will extract will later appear in many other applications and in many other contexts, either similar systems or not just field theory, but in all of string theory. There's a lot of analogies to these things. So we started by yesterday morning with the non-renormalization theorem in West-Zumino models without gauge fields. And we gave what I think is a conceptual explanation of why there is a non-renormalization theorem rather than the technical perturbative thing. We also showed this understanding also allowed us to see how it could break down. It could break down when some of the symmetries we use is no longer a symmetry. Once we have fewer symmetries, we have more options to write terms in the superpotential. And indeed, when we studied SUSY QCD, we showed that a certain term is generated. But we started understanding SUSY QCD without matter fields, just the gauge fields. We postulated the law, which we later justified. And we derived a Lagrangian, an effective Lagrangian for the pure gauge theory. And we showed that it's relevant for computing tensions of domain walls and so forth. So this is a physical quantity. And then we use this expression in other systems to derive the answer when there are matter fields. And the picture we had in mind is that we start with matter fields that are very heavy, so we can integrate them out basically at one loop. The one loop approximation is exact for the superpotential or for chiral quantities. And then we derived an effective action, which can be thought of as a 1pi effective action, including the normalization, which was for the meson field. So we had a meson field M, and we derived W equals NC minus NF, eta over det M, 1 over NC minus NF. And we show that this expression, first of all, is the unique expression invariant under all the symmetries in the problem and holomorphy. And the coefficient was also determined using this story. I said what can be computed and what is not, what is scheme dependent and what is not. But this expression led to some puzzles. First of all, when we turn on masses, so we turn on masses by just adding plus trace little m big M. This is a mass matrix in flavor space. And we solve for M. We showed that when the number of flavors is too small, the limit is singular. That was the first puzzling thing. The second puzzling thing was that we have this fractional power. Couldn't quite understand that. And later, when we send M to 0 for larger number of flavors, the answer depends on what limit we take. Different limits give us different answers. That was just a property of, I wrote the expression, and which also looked puzzling. So now we would like to interpret the same thing, the same phenomena, in the limit that the mass is very small. And there I emphasize that one should really focus on the classical theory. We start with the classical theory, and we analyze it. There's a classical potential, and the classical potential has flat directions. So we interpret them as being moduli spaces of vacua. So that was true semi-classically. We had these moduli spaces of vacua. And then we considered this, the non-perturbative dynamics, and we showed that for NF less than NC, we can interpret this W effective as a Wilsonian effective superpotential on the moduli space of vacuum, on the classical modular space of vacuum. So recall at very high energies, we had an SUNC theory with some quarks. And we go down in energy of the order of the waves of the quarks. Go that energy, the gauge symmetry is spontaneously broken. There is a Higgs mechanism. The gauge group is broken to a subgroup. We go down in energy. This subgroup becomes strongly coupled. And by the time we are in the extreme infrared, we have only these moduli, M, but there's an effective superpotential for them. And there is a potential that looks like that, and it has supersymmetric vacua at 1 over m to some power, negative power. So that as we set m to 0, as m goes to 0, there is no vacuum. I would really like to emphasize, since all of us are interested in string theory, that very similar things happen in string theory. There are moduli space of vacua classically. They exist semi-classically. It's very interesting to know what is the dynamics that can lift this degeneracy. Is there such dynamics or not? And this phenomenon of running away to infinity turns out to be rather generic, and for a good reason. Because as we move far out along the flat direction, the theory becomes more and more weakly coupled. Because as we move out, because of renormalization group, far out along the flat direction explores the UV. Fields are large, we are at high, it's like high energies. The theory is weakly coupled, and when it's weakly coupled, the classical approximation becomes better and better. And as it becomes better and better, the potential that lifts the classical degeneracy will be smaller. And therefore, when there's no mass, we run off to infinity. And fortunately, this exact expression that we had here told us about that without doing a computation. This expression was smart enough to know that for NF less than NC, there are classical flat directions and there is runaway to infinity. And it knows that by analyzing the theory with large mass, which is a bit surprising. So that's what we did. But this interpretation that we give this formula cannot persist for larger number of flavors, for a number of reasons. First of all, consider NF equals NC. The exponent here is infinite. So this expression doesn't make any sense. That's the first problem. When we take the derivatives and look for the expectation value, that's a good expression. Second, for the number of flavors bigger than the number of colors, I said that the rank of the matrix M is restricted. So classically, so now we start discussing NF larger or equal than NC. Classically, the rank of M is at most NC. And therefore, the matrix M classically can be brought to a form like this, with zeros here. So its determinant is 0, and it cannot be in the denominator. Sorry, the expression for NF bigger NC, M, that M is in the numerator, but the whole thing is 0. It's 0 and very singular. The next thing that is wrong for NF bigger than NC is that the exponent here is negative. So that means that the answer is proportional. This answer that we derived as the exact answer is very strange. Eta scales like e to the minus 1 over g squared. The minus is actually an 8 pi squared over g squared. So it's non-perturbatively small. If we just take this expression literally for NF bigger than NC, we have eta in the denominator. So this expression becomes more and more strongly coupled, more bigger and bigger as the theory becomes more and more weakly coupled. This makes no sense. So we know that whatever it is, the interpretation of this expression as a Wilsonian effective action is incorrect. So our goal now is to know, what does this expression mean? How can it be that we have this thing? We know that it has to be there because this is the thing that gives us the expectation values. So let's start asking ourselves, what can the Wilsonian effective action be? So we said that there is a moduli space of vacua, classical, which is parameterized by some m's and some b's and some b tildes, modulo some relations. So for example, for nf equal nc, these are numbers, and that m we said is bb tilde. So this is an example of a relation. So this is the space of classical vacua, and we ask ourselves, is there a possibility of generating any superpotential on that space of vacua for any number of flavors bigger than colors? And the answer is obviously no. There is no function we can write that would do the job. Proof: we already argued that this expression on top is the only expression invariant under the symmetries. And since this one does not have the right limits, it cannot be the right answer. So we conclude and since we concluded that, it means that the vacuum degeneracy cannot be lifted. This is a very powerful result. And I got to say, quite surprising if you're not used to that. We have this accidental degeneracy. In non-supersymmetric theories, there is never an accidental degeneracy. In the supersymmetric case, it's violated non-perturbatively. So that was kind of consistent with our intuition that there's no reason for the degeneracy to survive. But if we have enough flavors, the degeneracy survives. And there is no symmetry that guarantees that. Again, this is very common in string theory. We have many compactifications, moduli space of vacua, and non-perturbatively, the vacuum degeneracy remains. We have family of inequivalent solutions. And this is another example of this thing happening. It typically happens with more supersymmetries, because then the larger amount of supersymmetry guarantees it. But in this case, we have it in n equals 1. This fact also explains some other puzzles that we saw before. I argue that if we take the mass to 0, we just take the 1pi expression that we had before, solve for big M, I can write the formula, and take little m to 0 in different directions at different rates, we end up with different answers. From this perspective, this is not surprising. This is the consequence of the fact that we have this moduli space of vacua, and depending on how we set for generic masses, non-zero masses, we have isolated vacua. And then as we turn off the masses, we land on different points on the moduli space of vacua. So depending on how we tune the masses, we have different vacua. So we explain this fact. But what does this expression really mean? And how can it be that if we take this theory that has a degeneracy of vacua, imagine we turn on masses for some of the quarks but not others. We should be able to flow down, in the Wilsonian sense, to the expression we understood with fewer flavors and its effective superpotential. Are there any questions so far?
Yeah. So are there any proofs that this fact about the extended supersymmetry?
In extended supersymmetry, the question here, there could have been a superpotential, because the n equals 1 supersymmetry allows a superpotential. And it just happens to be the case that because of the details, there is nothing that is consistent. With higher supersymmetries, there isn't a superpotential. So there are things that look like a superpotential in n equals 2, but they are really related to the kinetic term. So only if you write them in n equals 1 language do they look like a superpotential. Otherwise, they are conceptually in n equals 2 language, they're partners of the kinetic term. So there's no arbitrary superpotential you can write down. No, it's a general property of extended supersymmetry, and it has been articulated. I learned it to see uncover my age with this shirt, and it's actually worse than you think because I wasn't a student that year. When I learned the subject, it was already kind of well known, so I cannot even pinpoint the reference.
I mean, the reference is, I always go to your paper with Ed, which is not.
We quoted it there.
You quoted it there.
Yeah, we were not the first to say that. In fact, this result was used. Which paper we did?
The first which had the long.
The n=2 paper. Oh, we actually used that fact maybe 10 years before that in another paper. So that's why I didn't ask you which paper, saying that there's no superpotential in n=2 in type 2 compactifications of Calabi-Yau. So it's the same fact if you write consider type 2 theory on a Calabi-Yau manifold, there's n=2 in 4 dimensions. And there's a question, can the vacuum degeneracy be lifted? And the answer is no, because in n=2 there is no superpotential. So we said it there. I think it's 85, 86, 7, around that time. But even then, we use a known fact. So that gives you an upper bound on how old it is. But it does not make it less true. Yeah, that's actually important. That it's a misconception of young people that the best things are the things that were done last month.
That's actually the way the Google algorithm works. Which is sad.
Well, for news, this is probably true. For learning physics, it's not.
So this K that distinguishes the vacuum, how do we interpret that?
It's the expectation value of, you mean in SUN, in the pure gauge SUN? I don't know what you mean. It's the expectation value of the gaugino condensate. The theory has a symmetry. So I'm hesitating a little bit. I'll give you the naive answer. The naive answer is that the theory has a symmetry, the ZN symmetry. So all the vacua are exactly the same. So if you sit in one of them, you can't say, this is k=5, and yours is k=3. What you can only make sense of is the relation between two vacua, the difference between them. Having said that, I will not explain why, but this answer is slightly too naive. But let's leave it at that. So we have this puzzle. All these questions point in the same direction. We have this modular space of vacua. In the quantum theory, we still have a modular space of vacua. And if this is the right answer, how can it be, and there is no superpotential, how can it be that if we turn on masses to some of them, we did it in the high energy theory, we should be able to do it in the low energy theory, and write something in the low energy theory such that when we turn on masses, we flow to this superpotential that we know is right in the Wilsonian theory. So a low energy observer should have something in his or her low energy theory that tells him or her that if you turn on masses, you will flow to this superpotential. And I'll give the answer, and then we'll check that it gives the right answer. So thinking about the puzzles is always a good way to orient yourself to the answer. So we'll focus first on NF=NC. And we said that classically, we have a relation. So this is the space. And on this space, we have some metric, classically, which comes from the Kähler potential. And at tree level, it's relatively simple. There are radiative corrections that make it more and more complicated. The claim is that in the quantum theory, this answer is modified. This is our same friend Ada. So first of all, we can check that this is consistent with all the symmetries that we had. So that's the first check. Otherwise, we would have rejected it right away. Second, what does this change of the equation mean? Classically, we have some space of M and B's. This is a multidimensional complex space. It's hard to draw it. But we can draw it as two cones. something like that, touching at a point. And there's a singular point at the origin. For example, let's take a model of this. Imagine you have the space xy equals 0. So xy equals 0, if x and y are complex numbers, are two cones which look just like that. On one cone, x equals 0 and y is arbitrary. And in the other cone, it's the other way around. Now we can deform this cone and imagine a little bit, it's slight deformation in the equation. We put epsilon here. What does it do to the cone? So we had these two cones. And now we make the space look like that. Sorry, I misdrew it. Okay, that would be one example. It's hard to draw in 2 dimensions. But it removes the singular point. Think of it as classical equations, then it's easier. With classical equations, this thing is 2 lines. And if I deform it with epsilon, we have 2 hyperbolas, depending on the sign of epsilon. If these are complex numbers, the space still remains connected. This slice, this real slice, makes it not connected. But the important thing of this epsilon is this is a deformation of the complex structure of the space. And the important thing about it is that it smooths out the singularities. So the space with this deformation is smooth. So this is a caricature of what the moduli space is. This is the right answer. So the moduli space, which had singularities before, becomes smooth. So classically, we had a singularity at the origin where the gauge group was unbroken and there are more massless particles. In fact, in general, singularities on the moduli space of vacua are associated with new massless particles that are there and not elsewhere. Again, this is a common thing. This is a kind of a general law of nature. Whenever you have a smooth modular space of vacua, at some point there is a singularity. If there is a singularity, there must be something there associated with that, and that's typically new massless particles. New massless particles, new gauge symmetry, and so forth. Here we see that happened classically, but the quantum theory managed to smooth it out. So the quantum theory does not have a singularity. The space is completely smooth. So I haven't yet proven that this is right. I'm just posting the answer and then saying what are the properties of that. The second, in particular, the point m equals b equals b tilde equals 0 is in the classical space, but not in the quantum space. There is no point in the quantum space where all these order parameters, m, b, and b tilde, all these coordinates vanish. And therefore, the symmetry, the global symmetry, is necessarily broken. This is an example of what in old-fashioned quantum field theory is called chiral symmetry breaking. We have strong dynamics. There's a symmetry of the problem. It's not violated non-perturbatively. The symmetry is still exact, so it's not explicitly broken, but it is spontaneously broken. And there is a nice smooth space. On every point in the space, the symmetry is broken. At different points, it is broken to different subgroups. So how should we think of a space which looks like that? Once we have such a constraint, the easiest way to think about it is to add a Lagrange multiplier for the constraint. So I'm adding a Lagrange multiplier. And I say that we have, this is the classical problem. And then I'm adding here minus eta as the quantum problem. So this is the claim the space-time superpotential. And this is something a Wilsonian person can consider, except that this has 2 modes that do not correspond to a massless mode. So strictly speaking, this is not a Wilsonian action because we added 2 modes. Which modes? X, the Lagrange multiplier, and the mode from here that doesn't satisfy the constraint. You should have heard that already in your calculus class. Whenever you have a complicated constraint, you can work on the constraint surface, or you can add more degrees of freedom that are not really there, the Lagrange multiplier, and then solve a bigger problem, which has the Lagrange multiplier and the modes that do not satisfy the constraint. And that simplifies life, but you should remember that there is no unique way to do that. There's more than one way to do that. And here we just picked one way. This is characteristic of non-Wilsonian actions. We threw in some massive field only to help us describe the massless dynamics. But this is an effective way of describing the dynamics. And with this way, we can now turn on masses. The same way we did before. And I leave it as an exercise for you to work on this constraint with this space and with this Lagrangian and solve for M and reproduce the answers we had before. So if you want a Wilsonian description, this is not good. In fact, there is no superpotential on the moduli space of vacuum. This is the best you could do. In fact, we had yesterday another expression with this field S that which I also emphasized was not a massless field. This is not a glue ball. This is a massive field. It's not a glue ball, a specific massive field in the problem. It's a field that we added. Its expectation value has some meaning. It's more of kind of a 1PI description. And this X is a cousin of the field S that we had before. There was some logarithm. The expression was more complicated. But this is a characteristic with Lagrange multipliers. There are various ways of adding them. They do the same thing. We can offer more checks for this expression. Well, this expression in this ansatz is consistent with the symmetries, consistent with holomorphy. We threw in one more variable x, but that's the price we had to pay. And we can have more checks of it by considering various special points. For example, we can go to the special point b equals b tilde. M equals 0, and b equals b tilde equals minus eta to the 1/2. Hope I got it right. Let's put more generally. b tilde equals minus eta. So on that subspace, baryon number symmetry is spontaneously broken, but the various flavor symmetries are unbroken. U1 baryon is spontaneously broken. There is another space we could consider. B equals b tilde equals 0, and that M equals eta. This is another nice space. Here, the SUNF cross SUNF is broken to a certain subgroup, depending on what M is, but baryon number is not, is unbroken. This is similar to what we see in ordinary QCD. So this is a model of chiral symmetry breaking for QCD. Specifically, if we let M be diagonal, so for example, if M is proportional to the identity matrix, it's broken to the diagonal SUNF. This is what QCD gives us. So this is a model for what QCD does. But that's true in one vacuum, but not in others. Now, there is a powerful constraint on the dynamics of field theories due to a 't Hooft, known as a 't Hooft anomaly matching conditions. And whenever we have an unbroken global symmetry, the first thing we have to check is that this constraint is satisfied. Is this part of the curriculum in any of the courses that you took? Should I review it? Or just state it? Yeah? Okay, I'll review it. So imagine you have a system that has a global symmetry. So that's an aside. We have a system with a global symmetry. And for simplicity, let it be continuous. So we have some continuous global symmetry, and it has some current J mu. We could try and couple it to gauge fields and gauge the symmetry. But there's often an obstruction to doing it. We compute a triangle diagram of these J's. And this triangle diagram can be non-zero. So there's a specific tensor structure that could be there. And that makes the gauging inconsistent. We already talked about global symmetries that are anomalous. This comes from one global current and two gauge fields. We have a similar phenomenon, which is actually more elementary. Three global currents can exhibit a similar anomaly. This is an obstruction to gauging the symmetry. So that was understood in the 70s, perhaps even earlier than that. The new thing that 't Hooft introduced was that even if the symmetry is global and we cannot gauge it, we can imagine adding additional degrees of freedom that would exactly cancel it, very weakly coupled, and such that we can gauge the symmetry. So everything is very weakly coupled. We have a strongly coupled field theory, which we're going to analyze, and we couple it to very, very weakly to external back gauge fields, and we throw in additional fields to cancel this anomaly. Now we go to the infrared, and if in the infrared, we should have a similar description. There's a Wilsonian description of the original theory we started with, and it's coupled still to the same, weakly coupled to the same external gauge fields, and the spectator gauge particles that we added just go along for the ride. The original theory was consistent, the anomalies were canceled. The macroscopic theory should also be consistent, the anomalies should be canceled. And therefore, we know something about the anomaly computed with the macroscopic particles. So now we can throw away the gauge fields that we added and the spectators and all that. And we learn from that that this computation in the UV should be the same as computing the same quantity, the triangle anomaly, in the IR. This translates to a group theoretical constraint on the quantum numbers of the particles, on the representations. And I'm not going to do it here. It's a rather elaborate calculation, especially if you're not used to that, with the table of quantum numbers that I had before. And if you go to various special points on this moduli space of vacua, you can work out the spectrum of light particles at that point, how they transform under the symmetry. And sure enough, all the anomalies match. This is a highly non-trivial constraint on our statement, on our proposed answer, that this is what happens. So far we explained some of the puzzles. We explained why, as we take the mass to 0, we land on different answers. That's because when the mass is 0, there's a modular space of vacua. We also demonstrated that the vacuum degeneracy might not be lifted. And by writing this expression, we explained how, despite the fact that the vacuum degeneracy is not lifted, we could still have a superpotential on that space. It's actually a superpotential on a bigger space in such a way that when we turn on masses, we reproduce the previous answers. So one thing that we see here is that we have to add degrees of freedom that do not satisfy the classical constraint. Recall that this classical constraint was just a property of every configuration in the functional integral. M was QQ tilde, B, so let me remind you where this came about. M was QQ tilde, B was det Q, and B tilde is det Q tilde. And the determinant of this is this times that. This is a property of matrices. And as I said, this is true for every configuration in the functional integral. And now the claim is that, first of all, we have to write a Lagrangian of fields that do not satisfy any constraint. And even if we go to the low energy theory, where the constraint should be satisfied, the constraint is modified. Now, such a thing is always surprising when it happens, because you have an equation that is true for every configuration in the functional integral, but is not true for the answer. So depending on your background, you have seen that in various places. One place this is often used is in two-dimensional field theories like the Cpn model. Does this ring a bell to some of you? Okay, so this is the problem with analogies. It helps some people, but confuses others. So I'll just mention, for the sake of the people who know this story, there's a similar thing there. There's a classical constraint. It's modified quantum mechanically, and all the dynamics follows from that modification. In fact, that case is not that different than what we see here. So you could still ask, so what's wrong with the argument that it's true for every configuration in the functional integral, but not true in general? So the point is that just thinking of the functional integral and manipulating it naively, this is true classically, but not correct quantum mechanically. One needs to regularize things. And when you regularize things, you have to leave out some things. Some things that you thought were true are not true in the regularized theory. And by the time you finish, most of the things you thought are true remain true, but some of them have been lost. So this is one of them. One of the things that you thought is right, because it's true for every configuration, but is not actually right. So we would like to keep marching up with more flavors, and I'm not going to do it in detail. I just state the answer. So for NF equals NC plus 1. We just go one step up at a time. And in this case, I will just state the answer. And the answer is that in this case, the cast of characters is M, which has indices flavor and flavor tilde, and B, which has one index F, and B tilde, which has upper index F tilde. So this is Q, 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 and there are NC of them, and NF plus 1, so there are many flavor indices up here when we bring them down with an epsilon tensor. And the claim is that in this case, we get a superpotential 1 over eta B F M F F tilde B tilde. There's a misprint here. Minus that M. The claim is that this is the answer. And you can run through all the analysis that we had before and check that everything works. First of all, we have to enlarge field space by a lot. Second, the classical moduli space of vacua is actually the same as the quantum moduli space of vacua, and it's a space of all m's, b and b tilde, subject to two relations. One of them says that b f b tilde f tilde is that m 1 over m f f tilde, and the second is that m f f tilde b tilde f tilde equals m f f tilde b f equals 0. So a classical person would say that we have these quarks, and out of the quarks we form the bilinear M, and these multilinear Qs, baryons and antibaryons, and they satisfy equations which follow from nothing but Bose statistics of the constituents. So these are the kind of equations that are true for every configuration in the functional integral. Also, if you look for the solutions of the flat directions, these D-term equations, I said before that you either solve these equations and you mod out by gauge transformations, or you write all gauge invariant polynomials in the original fields, and all gauge invariant polynomials are the ring. It's a ring generated by these, subject to these three relations. Now, the quantum person gives a totally different interpretation of the same story. The quantum person says, or the low energy observer says, we have a superpotential like that. We have many more fields than the classical person thought there are. Is all m and b tilde with no constraint, but there's a superpotential. And the stationary points of this superpotential are precisely these classical equations. So that's something you can check. Furthermore, you can check that this satisfies all the equations, all the quantum numbers that we had before. And the next thing you can do is turn on masses to some of the quarks, integrate out all the massive guys, and flow to all the previous cases we worked out. Finally, you can go to the origin of moduli space, go to the point m equals b and b tilde. All the terms here are cubic or higher order, so ignore the mass. Cubic or others, so everything is massless. So a low energy person on the origin, in this description, sees massless b's and massless m's. No symmetry is broken, and since no symmetry is broken, you have to check the 't Hooft anomaly matching condition, and they miraculously work. And as you go up There are more and more equations to check, and the miracle looks bigger and bigger. So what do we see here physically? We start at low energy with some gauge group and some matter fields and some flat directions. At low energies, the gauge group is gone. That's confinement. The flat directions remain. The topology of the flat directions remains. This is unlike the previous case. But the particles that the low energy observer sees are totally different. There are no gauge fields. The gauge fields are gone. M and B tilde appear as particles. And their numbers is bigger than what a classical person can think. Because classically, they satisfy some constraint. Quantum mechanically, they don't. So this is a phenomenon that can be described as confinement. No chiral symmetry breaking. So we don't have the chiral symmetry breaking. But we have massless particles, composites. And it's very surprising. It's surprising because this baryon appears to be a very complicated object. Imagine n being 1,000, so it has 1,000 constituents. Yet, it manages to be a massless particle at the origin. This is really surprising from the point of view of strong dynamics. You take something that is strong dynamics, and the first surprise is that you can actually say what's going on. And the next surprise is that you have this simple picture with elementary, what appear like elementary chiral superfields with some non-trivial interaction. We also see here eta in the denominator, which I complained about before. Well, we shouldn't complain about it here, because a classical person would say that it multiplies 0. Because classically, what this thing multiplies is 0. And therefore, there is no puzzle here. Alternatively, we can just say that to properly normalize these guys, such that their kinetic terms are canonical, we can absorb eta in them. So we see here an answer which manages to satisfy all consistency conditions. If you assume this is the right answer, you derive everything else. If you turn on the masses, you derive our starting point, the superpotential over there, which also shows that it's right. So if we take this thing and we deform it in any way we know, we always land on our feet. Any questions? Yeah. Yes.
If I turn mass center and bring it out, then I'll go back to the region of the previous case.
Yeah.
How can I see the...
Excellent question. So you can actually do that and let M be, M is a matrix. So call it mu and 0 everywhere else. Right, so turn on mass for one of them. I give it as an exercise for you. Turn it here. So I can almost do it in real time. So we have 1 over eta b m b tilde minus det m plus mu m and f and f. The index m had 1 upper and 1 lower index, 2 upper indices. Right? Where this is a matrix and this is a matrix and these are vectors. Integrate out this guy and integrate out m I and f and m and f I, and you will find the cast of characters in the lower energy theory. And you'll know that you get the right answer if you reproduce this. So this is the exercise I leave you to do. No, you cannot. So this formula contains more information than the classical one. That's the correct thing at low energies. Yeah, and the quantum one is different than the classical one. In this case, the stationary points are the same, but for different reason. Classically, the zeros of the potential came from solving the d-term equations, and here they come from solving an f-term equations of a different of a different problem. So what's D term, what's F term? It's in the eyes of the beholder. Whether you should view it as a gauge theory, a short distance, or this theory of chiral superfields, like a Wezumino model. One of them is better in the UV, the other is better in the IR. But yeah, that's it. So this brings me to the next step up, which I think is the most interesting. We just have to collect all the pieces and have one more intellectual jump, and then everything falls in place. So I'll write it here. So I'll again just state the claim and then state the checks. And for the rest of the talk, I'll have a long, long list of consequences. So the claim is that our original theory we started with. So our goal is to understand what happens for NF bigger than NC plus 1. We're kind of marching our way up in the number of flavors. So original theory was a theory with an SUNC gauge group with NF Qs and NF Q tildes. And our goal is to understand what this theory does in the infrared. So we claim that there is another theory Q. So this is a different theory. It's also a gauge theory. It has some SU gauge group. It has some quarks and anti-quarks, and elementary fields M, which are in NF square representation. I let them have dimension 2, because I'm going to identify them eventually with these M's. And this and that have dimension 1. In order to match the dimensions, I throw in another scale here, 1 over mu, which can be absorbed in the fields. And I also throw in a superpotential. And it's an exercise that I'm not going to do on the blackboard, is to work out the quantum numbers of all these theories. Ask, what are the global symmetries of this theory? And what are the quantum numbers of the fields, given that we have this superpotential? And the answer is that it's exactly the same as in this theory. So these two theories have the same global symmetries. And M in this theory is the same as M in that theory. And B tilde, that is of the form Q's, and this is of the form Q tildes, is the same as a B that I form here with Q tildes, with Q's, and B tildes with some Q tildes. This is already surprising, because the number of colors in the two theories is different. The number of colors is different, and therefore the number of quarks we have to put is different. In the baryon is different. Yet, this guy and this guy have exactly the same quantum numbers. So I'm not going to work it out in detail. So the claim is that these two theories are actually the same in the infrared. This is known as duality. The gauge fields and the fundamental quarks of this theory are related to the gauge fields and the quarks in this theory in a very complicated non-local way, which we don't understand. Yet, there is no doubt that this statement is right, and these two theories are in fact the same. And we can subject this to many, many tests. We can turn on masses here. So here we turn on trace M Q Q tilde, which is the same as trace M M. On this side, we just add a term linear in big M, because M is an elementary field. Here M is a composite field, and here M is elementary. You can do that, turn on masses for some of the quarks, flow down, and reproduce all the previous answers. I'm not going to do it here in detail. The second thing we could do is examine the flat directions. These two theories have exactly the same modular space of vacuum. But what appears classically on one side is quantum mechanical on the other. So this takes a little bit of work, because what's subtle on one side is not subtle on the other. In addition, there are these global symmetries. So I said that one has to check the 't Hooft anomaly matching condition. And since we have many more fields and many more symmetries and the charges are more complicated, the magic looks bigger. And again, this thing works, and it passes that in flying colors. It turns out that the eta of this theory and the eta tilde, which is the scale of this theory, are inversely proportional. So eta tilde is, there's a scale mu here raised to some power. So as one theory becomes strongly coupled, the other becomes weakly coupled. So it smells more and more like electric-magnetic duality. In this theory, the rank of M was restricted because this was a property of matrices. It was restricted to be at most NC. In here, M is an elementary field whose rank is not restricted at all. Let's examine what happens if we explore the range in field space where M is generic. So explore generic M in this theory. So we turn on arbitrary M, we forget everything else. Just looking at this term in the superpotential, we see that this generic M gives masses to the Q and to the two Q's here. I need a tilde here. Sorry about that. So it gives masses to all of them. So then on this side, I'll call this side the electric side, and this side the magnetic side. On this side, when I turn on generic mass, all the quarks disappear. So all Q's and Q tildes are massive. We can integrate them out and get some low energy SU, some low energy theory, which has some eta tilde low, which is like proportional to eta, and that M, which is the mass matrix over mu. The details are not important. The important thing I would like to emphasize, this is tilde. The important thing I would like to emphasize is now this gauge group becomes strongly coupled. There is gaugino condensation. And gaugino condensation in this magnetic gauge group leads to a superpotential So we rederive the same answer now from a totally different point of view. So recall that we first derived this answer by giving the original quarks very high mass and integrating them out and using gaugino condensation in the low energy theory. Then for low number of flavors, we explain that as a term along the flat directions. Now we give masses to all the magnetic quarks by turning on generic M, and we derive the same answer from gaugino condensation in the magnetic gauge group. And since the eta of the magnetic gauge group and the eta of the electric gauge theory are inversely proportional, the fact that we had eta in the denominator originally is no longer surprising. It's really eta in the numerator in the magnetic theory. So I'm not going to present more details about the tests of this statement, but I do want to talk about the consequences, because I think the consequences are quite surprising. We found gauge fields here out of nothing. This is the one-line summary of what we found here. We started with some gauge fields, SUNC. These gauge fields are completely gone. And what the low-energy observer sees is these other gauge fields. More precisely, depending on how many flavors and colors we have, the picture is a little bit different. Is this dark here? It is dark? In this range, so whenever the number of flavors is less than 3 times the number of colors, we have asymptotic freedom. So we start in the UV. This is the UV. This is the UV. With the electric theory, and we flow down. So this is the electric theory. For this range of numbers of flavors and colors, you can plug it in the formula there. The magnetic gauge group is also asymptotically free. So we can also start in the magnetic theory in the UV, in this case. And the claim is that both of them flow to the same point, which is a non-trivial CFT, actually a superconformal field theory, also known as Banks-Sachs theory. Banks and Sachs did it in non-supersymmetric theories. So that by itself is not that surprising. This is the phenomenon known as universality. Very common in condensed matter physics. We have 2 different field theories flow to the same fixed point. The fixed point is interacting, so we cannot say that it has some gauge fields or not having gauge fields, because it's some complicated conformal field theory with some spectrum of dimensions. No gauge symmetry is here. It is still interesting that we understand these 2 different fixed points, two different free field theories that flow to the same fixed point. But this case is the most dramatic, because for this range of numbers of flavors and colors, this theory is asymptotically free, and this theory is not. So in this theory, in this case, in the infrared, we flow to the magnetic theory. Of all the things I told you and all the surprises and all that, this is probably the most surprising, at least from historical perspective. Because we start from some gauge fields at low energy. So what do we do in QCD? We start at low energies with some quarks and gluons and some gauge fields and asymptotic freedom and deep inelastic scattering and all that. Become strongly coupled. And in the infrared, we find pions. And they got pions in the infrared because there's chiral symmetry breaking. These are the Goldstone bosons. Here, what we find in the so we start in the UV, something that is not that different. Okay, it's supersymmetric, but that is not that significant here. We have gauge fields and some matter fields, and we flow to the infrared. And what we see in the infrared is not pion, not just chiral superfields, but we also find gauge fields. Gauge fields which have nothing to do with the UV gauge fields. They came out of nowhere. In fact, there's a general theorem that if you have a global symmetry in the UV, it cannot become a gauge symmetry in the infrared. It's relatively straightforward with modern technology to prove it. So if we found a gauge symmetry in the infrared, it should better not start its life as a gauge symmetry in the UV. It should really emerge from nothing. So this is the phenomenon of emergent gauge symmetry. We start from something, we don't care what it is. We find in the infrared some composite gauge fields with exact gauge symmetry. Now, when I was educated many years ago, I learned that gauge symmetry is very fundamental, because all of nature is based on gauge symmetry, starting with Maxwell theory, and then there's Young-Mills theory and general relativity. We see here an example, not the first one, that gauge symmetries can emerge, and they are not fundamental. In one description, they exist. In another description, they do not exist. In fact, it's not even clear with all these dualities what's fundamental and what it's not. What on one side looked fundamental like the meson M, it's composite on the other side. So which degrees of freedom we think are the fundamental degrees of freedom? Even this question becomes ambiguous. Is it surprising that the gauge symmetry is emergent? We have a system that has no gauge symmetry to begin with, or has another gauge symmetry that is gone, and we end up with a gauge symmetry. Symmetry appears to be important. It acts on something. The point is that gauge symmetry is not really a symmetry. It's a symmetry of the equations, but it's not really a symmetry. More precisely, it's a redundancy. We introduce gauge parameters. There is a redundancy in our description, and that's true already in QED, and people fully understood that. In electrodynamics, we introduce the gauge symmetry in order to have a description of the system which is both local, unitary, and Lorentz invariant. So these are the three things that we would like to keep. And if you just go to the old literature of electrodynamics, you will see that you either work in axial gauge, where everything is manifestly unitary, but you sacrifice manifest Lorentz invariance, and then you have to work very hard to prove that it's there. Or you use a covariant gauge, like Lorentz gauge, where Lorentz invariance is manifest, but there you have to work very hard to prove that the theory is actually unitary. And the better perspective is that you throw in more degrees of freedom that you don't really need, these gauge degrees of freedom. Now the theory is manifestly unitary, manifestly Lorentz invariant, but the price you pay is having all this excess luggage. So you cannot say that the excess luggage that you got is the fundamental principle. And here we see it very clearly that it is emergent. Another way of saying it is that when we have a symmetry, the Hilbert space is in a representation of the symmetry. This is what a symmetry is good for. It acts on the states, and the states are in representations of the symmetry. We have operators. The operators are in representation of the symmetry. That's not true in gauge symmetry. Gauge symmetry doesn't act on anything. The Hilbert space is gauge invariant. In axial gauge, we have Gauss' law that tells us that the Hilbert space is gauge invariant. We are kind of constantly being reminded that we should only discuss gauge invariant observables. So we introduce the gauge symmetry, and then we say, but remember, discuss only those observables that are gauge invariant. So the gauge symmetry doesn't act on anything. It's not a symmetry of anything. So it's perhaps less surprising that it can be emergent. A related fact is that gauge symmetries cannot be broken. We often learn about the Higgs mechanism, and in the Higgs mechanism we have a gauge symmetry that is spontaneously broken. So the way this is usually being taught is that we start with a system without the gauge symmetry. There is a global symmetry. The global symmetry is spontaneously broken. And then there is a Goldstone boson. Then we gauge the symmetry, and the gauge field eats the Goldstone boson as its longitudinal mode, and everything becomes massive. And not only do we learn that, this is what happens in nature, and there are a number of Nobel Prizes for this discovery. But this description is quite good and very useful, and it's true in nature, but only when the theory is weakly coupled. When the theory is strongly coupled, this description actually does not make any sense. In fact, every sentence of the ones I made is wrong. Let's start with the fact that we have a symmetry that is spontaneously broken. As I emphasized, there's no symmetry to begin with. So there's no symmetry, so it cannot be broken. Another way to say that is that when you discuss spontaneous symmetry breaking, a crucial part of the story is that you are in infinite volume and you have an infinite number of degrees of freedom. In quantum mechanics, you don't have spontaneous symmetry breaking. If you have just one degree of freedom or a finite number of degrees of freedom, even in the double well potential, the true states are the symmetric or the anti-symmetric ones, rather than that you sit in one vacuum or the other. In order to have spontaneous symmetry breaking, you need to have an infinite number of degrees of freedom. And then there's this whole story about clustering, etc., etc. Now, the gauge symmetry, even if you think of it as a symmetry, it acts only locally. It doesn't care whether space is infinite or not, because it acts only at one point. That's the whole point of a gauge symmetry. It acts only locally here. And therefore, this whole story about spontaneous symmetry breaking is inappropriate for gauge fields. A, it's not a symmetry, and B, nothing is broken. And it is true, though, that it's sometimes convenient to use it. The next conclusion is that, how much time do I have?
Well, as you started late, so
Okay, but we all want lunch, so I'll finish now. It turns out that this example I mentioned here is not unique. And there are many, many examples already in field theory, and even more so in string theory, where I'm sure you heard about, where similar things happen. We can repeat this story here already in field theory for SON or SPN, or even exceptional gauge groups. For quiver gauge theories, enlarge the number of supersymmetries, n equals 2, n equals 4. And I can give a series of lectures about any one of them. The details are somewhat different, but the concepts are kind of the same. You look for the BPS quantities, or the chiral quantities, or the topological quantities, or the holomorphic quantities. They have different names. Look for flat directions. Check what happens to the flat directions. Check what instantons can do, because they could violate some symmetries. These techniques are basically the same, although they become more and more sophisticated with time. People compute all sorts of elaborate quantities. And the dynamical lesson, which turns out to be common, is this role of duality. So this is not an esoteric example. Most examples behave like that. This story is very similar. First, by changing parameters, by changing the gauge group a little bit, some integers change. But even more sophisticated examples, the n equals 4, or things coming from 6 dimensions, and so forth. So this turns out to be a typical example. And the story in string theory is very similar. It follows the same set of lines. Examine the classical theory, look for BPS quantities, check whether you can interpolate from weak coupling to strong coupling, and look for duality. So these are really the same principles in all these cases. So what I'll do in the remaining lecture, so everything I said today and yesterday, I said it in 95. Every single word. Nothing was modified except the order of the presentation was different. And what I'll do in the next lecture is show that some of these techniques with new interesting twists occur also in 3 dimensions. And there are a bunch of reasons to be interested in 3 dimensions. First of all, it's there. And second, there are applications for condensed matter physicists are very interested in phenomena in 2+1. They call it 2+1 dimensions. So when I say 3 dimensions, this is what they call 2 dimensions. And we'll see that many of the phenomena are the same, but there are also many new interesting things that happen and that are worth understanding. It's nice to see that some of the lessons that we learned here are also applicable in 3-dimensional field theories, but it's also nice to learn new things there. So this would be work that is a little bit more modern. So I think I'll stop here and ask if there are any questions.
So you called this a duality, and then you said that the duality was the statement that they flow to some similar theory in the IR. But when I think of duality off the theories are really the same. You want to believe the whole theory is the same.
Okay, so there are 2 notions of duality, which are actually very, very closely related to each other. The first is the duality that we see in n equals 4 super Young-Mills. This is a conformal field theory. So we cannot even ask what happens in the UV or in the IR, because there's no UV, there's no IR. They're all the same, because the theory is conformal. And the same conformal field theory has 2 different presentations. In fact, has an infinite number of presentations. This is notion number 1. Notion number 2 is like this thing, where it's only an infrared duality. So we have 2 theories that are the same in the infrared, either by both flowing to the same point, or one of them flows to the other. These 2 notions of duality are essentially the same. Because in many examples you can start assuming one and derive the other. So you can assume that this duality is right. It wasn't proven. There's a lot of evidence that it's right from many different perspectives, but it wasn't proven. Let's assume it's right. If you assume this or some of its cousins, the only infrared dualities, you can derive, say, the duality of n equals 4, or of other exact dualities, by doing something, turning on something, go to a special point in the moduli space, etc., and then flow to the infrared, and you can derive this thing. So these two dualities are really the same. And the fact that what's electric on one side becomes magnetic on the other side, weak coupling at one is strong coupling in the other. All these qualitative features are the same as in dualities. I did not talk about it here, and in this theory is actually not a good place to examine it, but in the SO version of this story, there's a notion of electricity and magnetism. And with electricity and magnetism, they are being exchanged under duality. So in that case, it's almost the same. You just say there's a U. Wherever there's a U here, just make it O, and maybe shift the integers by 1 or 2 here and there. So it's very close. And in that case, you can define electricity and magnetism. These are Wilson and 't Hooft lines, and they are mapped to each other appropriately as they should under duality. So yes, as you move from one example to another, some things are different, like this is an infrared duality and the other is not, but it's still, they're in the same tribe, if not in the same family. Any more questions? Yes. Well, what do you mean by derive? Okay, so anything that is not gauge invariant here does not flow. And everything that is not gauge invariant here does not map here. Only the gauge invariant information is mapped. So, for example, I showed that the meson from here, which was QQ tilde, that's gauge invariant, so that's good. We should better map it. And it's mapped to an elementary field. The baryons are composite here and composite here. So whenever you have a gauge invariant observable here, it's mapped to a gauge invariant observable here, and vice versa. The gauge non-invariant information does not match at all. And as I emphasized, that's okay, because the gauge non-invariant information shouldn't even be discussed in the first place. Now, whether to derive that, I don't know how to derive it. And it's a big challenge how to derive all these dualities. And I'm sure that the fact that we cannot derive that is telling us that we're missing something. At the very least, we should see if you look at the billion gauge theories. So let's take another example. Imagine you're just doing F mu nu square, this Maxwell theory. It has equations of motion d mu F mu nu equals epsilon mu nu rho sigma d mu F, what am I doing? Mu rho sigma, something like that, equals 0. That's the Bianchi identity, and that's the equation of motion. You can dualize that, and that you can actually prove, and transform that to F tilde mu nu square, where F tilde is the dual of that one. And then the equation of motion and the Bianchi identity are exchanged. This you can actually prove in the functional integral. It's like a Fourier transform in the functional integral. There's cousins of that in 3 dimensions, in the Ising model. This is an old story that was understood nearly a century ago in its most elementary form. The common thing in all these theories is that they are free. They are abelian. When it's non-abelian, something very similar is happening, and we don't know why. It's related to all sorts of deep issues in mathematics associated with Langland's duality. That it's connected to all sorts of different things. And it's mysterious. We know a lot about them, but still there's no elementary derivation. I'll be delighted to see a change of variables in the functional integral. Add fields, integrate something out, change variables, do all the standard tricks that we do that would take you from here to here. And believe me, I wasted a lot of time looking for such a thing. And with zero outcome, nothing. But maybe somebody bright in the audience will know how to do that. I can assure you that such a derivation will answer many, many questions and will lead to many deep insights. And I think that's not a minority view. I think many people think that if we had a good understanding, deep understanding of duality, including a real derivation, this would be a real breakthrough. Instead, people found all sorts of other dualities, which is great. ADS-CFT is even more sophisticated than this one. And they have increasing degree of sophistication. And yet, there is no actual proof. I feel that proving this and proving ADS-CFT will not be such a big... So if you do one, the other will almost fall into place immediately. Because the obstructions to proving are kind of similar. In free theories, in free abelian theories, it's simple. The Ising model is not free, but still the duality is more or less straightforward. In all the other examples, it's a free field theory. Oh yeah, tons of them. So let me give an example. Okay, I can't win. So we can start with an SU2 gauge theory, very much like the gauge theories we talked about here. But instead of having matter fields in the fundamental representation, let it be in the adjoint, with one quark in the three-dimensional representation. This theory happens to have n equals 2 supersymmetry, but that's not important for what I'm going to say, because I'm just viewing it as an n equals 1 theory. What's known about this theory? The story is very similar. We're going to follow the same route. We have to find the classical moduli space of vacua. So we find all the gauge invariant polynomials, which is just this. So there's one complex number. So it's a classical moduli space of vacua parameterized by one complex number. Quantum mechanically, the degeneracy is not lifted, very much like in all the examples I talked about before. Quantum mechanically, the moduli space remains the same, but classically we had one singularity at the origin where the full SU2 was restored. This was singular. In a quantum theory, instead we have two singularities, and in every one of them there is a massless particle and a U1 gauge field. So at the generic point in the moduli space of vacua, we have a gauge matter field in the adjoint. So SU2 is spontaneously broken to U1, very similar to the spontaneous breaking that we had before with SUN. We give a vev, it breaks to a subgroup. The same thing is true in the quantum theory. And in this case, there is one chiral superfield, phi tilde. Give it a name, not a name. M, and call it also M tilde. So they are charged under the U1. More precisely, they are charged under the dual of that U1. So here we have a situation, if we live somewhere here in the moduli space, that at short distance, we have SU2 with its 3, flowing in the infrared to U1 with U. Let me make it even closer to our notation. Call it M. This is the M plane. And there's a superpotential. Let's make the notation as close to what we had here. Tilde. So this story looks very similar to what we had there. We start with a non-abelian gauge group with some matter fields. We end up with a gauge group. It happens to be abelian. Some composite quarks. And the field M that was originally composite is now elementary in this theory. This theory is also n equals 2 supersymmetric, but that is not being used in this discussion. In this case, we identify these Qs as being magnetic. So in that case, we actually know that these are magnetic monopoles. But the story is very similar between these two. So you wanted an example where on one side we have abelian and the other side we have non-abelian. So here is one. There are tons of other examples. I think we should go to lunch.